Hello guys, good afternoon. And this problem is asked in the weekly contest of Leet-Code here, 380. Recent uh, Sunday's Leet-Code contest. Uh, the third question. It was the third question. Actually, the fourth question was easy. It was a KMP algorithm problem, and this third question was hard. This third question was hard problem, and I will explain you in a simple steps here. As many requested for this problem, so I have solved this problem and I'm going to post this problem at 4 o'clock, 4 p.m. And the problem is maximum number that sum of the price is less than or equal to k. So, okay, like uh, first of all, we will try to understand the problem statement here. Okay, like you are given an integer k and an integer x. Okay, given an integer k and an integer x. Okay, consider s is the one indexed binary representation of an integer num. So okay, so if there is a num called 4, then the binary representation of the number is 100, right? 0100, right? Have taken 4 bits here. Okay, so 0100 is a binary representation of a num 4. Okay, the price of a number num, the price of a number num is the number of i's such that I percentile x equal to 0, and si is a bit set bit. Okay, so I is nothing but here, like here this is a zeroth bit, and this is the uh, first bit, this is the second bit, and this is the third bit, right? So in this way the I is represented here. So if we, and we have to consider it as a one based indexing. So here the zeroth index will become 1, and this will become 2, this will become 3, and this will become fourth bit. Okay, so now what we have to do is, so uh, we have to the price of a number num is the number of i's. I is nothing but the bit, right? S- Such that I percentile x, I percentile x, x is given, right? X is equal to 0. It's nothing but if that index is divisible by x, then we have to consider it. Okay, and si, the ith bit is also a set bit. Set bit is nothing but, set bit is 1, right? S of I should be 1. Okay, so how many such of i's? Okay, so 1 percentile x is divisible by, so let us consider this, for example, if x is equal to 1. Okay, so 1 percentile 1 is equal to 0, right? But si is not equal to 0, not equal to, not a set bit, so we should not consider it. So 2 percentile 1 is equal to 0, yes it is, right? So we can consider this thing because it is a set bit. So price of a number will become how much now? Price will become 1. Okay, and for 3 it is also divisible by 1, and but si is not a set bit. For 4, 4 is also divisible by uh, 1. These are indexes of set bits. Okay, and uh, it is not a set bit. Okay, so the overall price of a num here is 1, right? Only one i's are there, by i's present, where si is a set bit. Okay, and si percentile, I percentile x is also equal to 0. Okay, so we understood the statement right here. We understood the statement here. Okay, now return the greatest integer num. We have to return the greatest integer num such that the sum of prices of all numbers from 1 to num is less than or equal to k. Okay, now what is this? So if we consider num, okay, so if we consider num, we have to consider num such that from 1 to num, the overall prices should be lesser than equal to k. Okay, so if we consider num equal to, if we say num is 6, okay, num is equals to 6, then from 1 to 6, so overall price of 1, overall price of 2, overall price of 3, overall price of 4, overall price of 5, overall 6. So we have to summate these all prices, and if these prices are less than or equal to k, then we can say that we can consider the number as a valid number. Okay, so we have to consider the greatest integer num such that the sum of prices of all numbers from 1 to m is less than or equal to k. Okay, see, uh, okay, here we'll take note of this. In the binary representation of a number, set bit is a bit of value 1. Okay, as I said earlier. Okay, and the binary representation of number will be indexed from right to left. Okay, from right to left. Okay, for example, s is equals to 1100, s of 4 equal to 1. Okay, 0 1 1 2 3 4, 4 is equal to 1, and 2 is equal to 0. From 1 2, here it is represented from right to left. Okay, from right to left, from right to left. Okay, in this way we need to consider the binary representation. Okay, now we have to solve the problem. Okay, so uh, now we will look at the constants here. Okay, so k can go up to 10 to the power of 15. Okay, k can go up to 10 to the power of 15, and x is equals to 8. Okay, so now we have to consider a num such that it is lesser than or equal to, such that the prices of numbers from 1 to num are less than or equal to k. Okay, so what we can do is we will do binary search here. Okay, we will do binary search, and we will consider a number. If that price is lesser than or equal to some the k value, we can consider that, and we will by doing binary search we will consider that number. Okay, so okay, we have to, for doing binary search we need to have some lower boundary and upper boundary, right? So our lower boundary will be 1, and our upper boundary, let us take 1e15. Okay, let us take 1e15 here as our upper boundary. Okay, okay, let us take 1e15 as our upper boundary. Okay, and we will find the number in between them such that the prices of all numbers from 1 to 1 to something mid is less than or equal to k. Okay, now the question is how to find the price. Okay, now the question is how to find the price. Okay, now we will consider some scenarios here. Okay, for example, we have to check the uh, price of 13 here. Price of num 13, that is price of num 13 means 1 to 13 numbers prices, right? So how we will be finding that number. Okay, so for knowing the price of num 13, we need to keep the track of the most significant bit. Okay, the leftmost bit will be the most significant bit, and the rightmost bit will be the least significant bit. Okay, most means it is the higher priority bit. Okay, higher priority bit will always be in the left side, and lower priority bit will always be in the right side, right? So what is the most significant bit of 13? Okay, we have to find the most significant bit of 13 here. Okay, what is the most significant bit? Most significant bit of that is how to find that most significant bit. Okay, see, now the bits representation are in this way, right? So for example, I will consider only four here. 2 1. Okay, these are the 4 bits, right? 1 2 4 and 8, right? These are the bits. The most significant bit will be for 13 will be, okay, we will represent the 13 in a binary representation form. So it will be 1 and 1, 0 and 1, right? So 8 4 12, 12 plus 1 13. Okay, this is the binary representation of a 13. So most significant bit of 13 is this, right? This bit, right? So most significant bit of 13 is 8, right? How to find that? Now how to find 8? Now uh, we know that uh, These all are the two powers, right? 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. Okay, so the most significant bit power will be 2 to the power of 3, right? Yes. So if we do logarithm of 2 to the power of 3 base 2 base 2, we will get the value of most significant bit. Okay, when we do this thing, we get the uh, most significant bit, uh, most significant bit. We will get the power. Okay, we will get the power, like how at what power it is, our most significant bit is lying. Okay, okay, we will get the we will get the whose we will get the power of the most significant bit. Okay, we will get the power of the most significant from power. How to get the value? If we do one left shift, the most one shift, one left shift, let us consider this as a value here. Consider this as a value. Then, if we shift left shift one time, then we get the value of the power of most significant bit. Don't worry, we will be live. We will be coding this all in the coding part. Okay, don't worry about this. So this is how we will be finding the most significant bit power and the value of the most significant bit. Okay, so if you observe here, this is the most significant bit, right? Why we are taking most significant bit, and why we are taking value of the power of most significant bit. Why is the question here, right? So if we consider this thing here, if you observe up to, like, from 15, it will be most significant bit will be 1 up to 8, right? We have to find the significant, how many ones are there in that, right? We have to find that thing, right? Here, how many set bits are there in the set bits are there from 1 to 13. We have to find that sum, and we have to find the, uh, like, basically we have to find how many set bits are there from 1 to the given number, right? Okay, we have to find that thing. So for that, I'm considering the most significant bit. Okay, this is the most significant bit. From uh, from here, how many ones are there can be said, like, how many numbers are there. So what is the value of the most significant bit? It is 8, right? So from 13 minus 8 plus 1 will be the most significant bit of index 3. That means, at this part. Okay, at this part, these many numbers will be there until 13 to 8. When we do, uh, so we will just do this thing here. So how many numbers will be there here? If we consider, so how many set bits will be at the third index from 13 to, how many such type of numbers will be there can be calculated as n minus val plus 1. With this formula, we can calculate the number of set bits in that index, right? Up to such number, we have to find this, and find this recursively here. How many, for this index, we can find that these many set bits are there in our, in that index. What about these all, like, uh, second index thing? This all can be find if you observe here from 13 to 8. Okay, so 13 to 5. Okay, 13 to 5. 13 minus 13 minus val is nothing but 8, right? 13 minus 8 is 5, right? Up to 5 we will be considering this thing, okay? So whatever it be, like if the most significant bit is 16, okay, if the most significant bit is 16, so we will be doing n minus 16. Up to that thing we will be considering the indexes, okay? If the most significant bit value is 4, then we will consider only that two values, okay, that four values, and we will keep on doing it recursively, okay? First, our for example 13, we got that most significant bit as the 8, right? So up to 8 digits, up to 8, from 13 to past 8 digits, we need to consider the we need to count the number of set bits, okay? From 8 to 5, if we want to count the how many ones are there in this range, 1 2 3 4 5 6, okay? So for example, if we want to calculate 14 here, so 14, 14 up to, from 14, 14th most significant bit is 8, right? So from 14 to 6, right? 1, from 14 to 6, 14 minus 6 is 14 minus 8 is 6, right? Up to 6 we need to consider the count, okay? So up to how many things we have? 1 2 3 4 5 6 7. Here we have 7 here. So 14 minus 8, 7. How much? 6 plus 1? It is 7, right? We are getting with this formula, right? So 13 minus 8. 13 minus 8 is 5. 5 plus 1 is 6. So from 13 to 5, how many set bits are there in the index 3? It can be done. It can be calculated using this formula. Okay. And coming to the inner indexes, like 2, 1 and 0 indexes, for what about that? If we observe here, if we calculate the set bits from 1 to, from 5 to 13, 1 2 3 4, 1 2 3 4, we have to consider, if we consider here it will be like, if we consider n minus 5, from here to here, from 5 to 13, if we consider the set bits, like if we consider the set bits 1 2 3 4 5 6, like up to, 5, up to 5 13, and we should not include 5 here. Up to 5, okay, up to 5 we should not include 5 here, okay? Up to 5 we need to consider the set bits in the indexes, okay? From it last indexes we got this thing, right? Plus 1. By doing this thing we can get the how many set bits are there in the last index, like, okay? For getting the how many set bits are there in inner indexes, we can do this thing. If we calculate this thing, 1 2 and 3 and 4, up to here only, right? Okay, there are four ones in index 2. And if how many ones are there in index 1? 1 2 3 4. In index 1 also there are four indexes, four ones, okay? In index 0, 1 2 3 4. In index 0 also there are four indexes, four ones only, okay? Now let us take another example here. If we consider 14 here, okay? So 14th 14th most significant bit is 8, okay? From 14 to until 6 we need to consider, okay? For up to here we get 1 2 3 4 5 6 7. 7 bits will be get we will be getting in 7 bits will be getting um, in last index, right? And inner indexes we will be getting from 14, 1 2 3 and 4, right? Up to here, 1 2 3 and 4, 1 2 3 and 4, okay? We need to consider, if we observe here, for outer indexes we are getting these many ones, and for inner indexes, we are getting val by 2, val by 2 set bits here. Okay, if we observe here, val is nothing but most significant bit, that is 8th bit or 4th bit or 2 second bit or 1 bit or 16th bit. Okay, if we consider 16th bit as our answer, then inner indexes will have 16 by 2. Okay, 16 by 2 bits in the inner indexes. Okay, for every indexes we need to add plus 4 plus 4 plus 4. Okay, val by 2 val by 2 val by 2, in this way we need to add them. Okay, up to here, uh, up to here we got the um, up to here we got the count of set bits, right? From for going to here, we need to we need to call the same function again, that is n minus val. If we call this function again, then we will be doing the same thing from here up to here. Okay, now for 5, if we consider 5, the most significant bit is 1, that is 4 here. Okay, now 4, from 5 minus 4, 5 minus 4 is 1. Up to here we need to consider the inner indexes. Okay, so 4 minus 2 plus 1. Okay, 4 minus 2 plus 1 is how many? 3. Are there 3? So 13 minus 13 minus 13 minus 8 is 5. From 5 we need to consider this thing, right? So uh, 4 for 4, how many we will be getting? 4 minus 4 plus 1, 5 minus 5 minus 4 plus 1, we will be getting these many set bits in the last index, right? So from here, if we consider 5 minus 4 is 5 minus 4 is 1. Up to here we need to consider the set bits, right? If we count 1 and 2, we are getting same, right? So for getting inner indexes, what we have to do? 4 by 2 will be, we will be getting how many? 4 by 2 will be 2, right? 1 and 2. Okay, and for this 1 and 2. Okay, is it okay? Now we have to consider also base cases here. If our n equal to 1, then we can directly say that there will be only one bit present, so we can directly do that thing like n00 plus. And if n equal to 2 here, we can directly do like there will be at most two bits, right? And 0th bit and 1 bit, so we will be just incrementing that thing, and we will be returning that. In other cases, we will be calling for the recursive solution here. Okay, okay, understood. This is the whole criteria here in this thing. We have to understand, if we understand this thing, then the problem is very simple here. This is the whole thing we need to understand here. Okay, now keeping all this in track, we will be considering we'll keeping all these notations in track, we will be solving this problem. Okay, so as I said, for what are the we have to do the binary search, right? So what are the lower boundaries and upper boundaries here? Okay, long L will be 1 here, and long R will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, long R will be 10 to the power of 15 here, and long answer will answer also final answer, right? We have to return the how many number, greatest number, right? Greatest number we have to return here. Okay, so we will be doing simple binary search here. L is lesser than or equal to R. Have to calculate mid here, same as the binary search. L plus R by 2. Okay, we have considered the mid here, and for calculating the set bit sum, we need to have the array here. Okay, we will be considering array here. I will be storing it globally. And for every iteration, for every binary search operation, we need to calculate the sum, right? So for every, like if we consider, so for example, there is a range from 1 to 20. The mid will be 10. Okay, for 10 we have to consider, we have to count the all the set bit number, right? Set bit sum, right? If we calculate the set bit number from, if it is greater, then we have to move forward, and we have to, uh, uh, like for every number we need to consider the array, right? So I will globally declare it, and I will initialize for every iteration. Okay, arr equal to new long. And to calculate this, so I have just used one formula here. So I have to consider how many bits I have to consider here. Okay, so 0th bit, 1th bit, 2nd bit, this in this way, right? So 2 to the power of 54 is nearly equal to 1e 15. Okay, that is 10 to the power of 15. Okay, so it is nearly equal to 10 to the power of 15. So I will just consider the 54 as 54 bit as my answer. Okay, 54 bits. I will be considering 54 bits here. Okay, so now, as I said, we have to uh, calculate the set bits which are divisible by x, right? Okay, and remember that it is a one based indexing. Okay, so we have to calculate those numbers only, those sets only. Okay, those set numbers only. Okay, so for calculating that, we will consider long val here equal to 0, and for int I equal to 0, I less than 54, I plus plus, if I plus 1 percentile x equal to 0, then I can consider this, right? Then I can store it in my answer, that is ARR of I. That's it. Okay. Now, if my val is lesser than or equal to k, okay, if it is lesser than or equal to k, then my answer will become med, and I will move to, and uh, I will try to calculate for the bigger number. If the number is satisfied, then I will calculate for the bigger number. Okay, mid plus, I will move my I to mid plus 1. Okay, from I to 10p, if 10 is lesser, if 10 uh, price is lesser than or equal to k, then I will consider from 10 to 20 here. Okay, I will check whether there is a number which is, whether there is a number which, where, whether there is a number whose price is lesser than or equal to k, from 10 to 20. Okay, or else I will just move my mid minus 1. If it is not, if it is greater than k, then I have to check for the lower number, right? If 10 is greater than k, then I have to check from 1 to 10, right? So just I'm doing the binary search here. Okay, at last I need to return answer it. Okay, now the main step here. Now we have to calculate the, so before 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 calculating this all, we need to call the solve function here, which takes mid as a parameter and calculates the number of sets in a array bit. Okay, which calculates the price of the number. Okay, so public void, and remember this is a recursive solution here. Okay, uh, long mid, right? Let us consider long mid. Okay, and now, as I said, we have to consider base cases, right? We will be considering these base cases. Okay, okay, and if n equal to 0, then it will just, we need to just return. Okay, if I, okay, we will be considering this as n equal to 1. Then we need to calculate. uh, Now, after if we consider one as our set bit, then it is a base case, right? For one, there will be only one set bit, so we will be incrementing that set bit, and we will just return from here. Okay. If n equal to two, okay, if n equal to two, error of zero, there will be two set bits, right? At the zeroth bit and first bit, right? We will just increment them and just we will return from it. And now we have to consider all the base cases. Now we have to calculate the most significant bit index value here. How to calculate that? Now if we consider MSB equal to, we can calculate in this way, like mat.log of n by mat.log 2. If we do this thing, then we will be getting that MSB here. Okay. Now we need to get the MSB value here. Okay, significant index value. How to get that thing? We need to left shift it by one. Okay, one unit. Val equal to 1L left shift by MSB. We will be getting this thing. Left shift operation is two two left shifts, right? Two left like lesser than symbols, right? We'll be left shifting it. Okay. Now we have considered the MSB and the val here. Now we have to uh, like how many set bits are there in the uh, last like MSB index. Like how to calculate that? Um, okay, how to calculate that? If we consider this thing like uh, long answer equal to n minus val plus 1. This gives the uh, number of set bits in the MSB index, right? We will be just incrementing that thing. Okay, equal to answer. And so int I equal to 0, I less than MSB. Okay, we have to consider all the lower indexes also, right? From 0 to up to until MSB minus 1, right? So we have to consider all that. For that, it will the number of indexes, the number of set bits will be uh, answer like the number of set bits will be val by 2, right? Like the MSB value minus value by 2, right? So for that, ARR of I plus equal to val by 2. That's it. Okay. If we do this thing, we will be getting we will be storing all the set bit sum, and at last we need to call the recursive function here, n minus val. We call this thing, we will be generating for we'll be calling for other like if we consider 13, 13 minus 8 will be 5. We will be calling for 5. From 5 it will be going to 1, and from 1 it will be getting return here. Okay, this is how we will be solving the set bit sum here. Okay, and we will be storing it their appropriate indexes. Okay. Okay, after calculating the thing, we will be calculating the set bits value at indexes which are divisible by x. Okay, we will be considering only those indexes. After doing that, we will be checking the conditions. If the conditions are matched, we will be storing it as an answer, and we will be moving more further. Okay, or else if it is not valid, if it is not with that answer, not matching with that answer, we will be moving little further. Okay, and from this here we will be calculating this answer. Okay, now we will try to run this, check whether there are any. Okay, integer number is too large. Okay, now we cannot consider like in Java, whatever the number we written, it will always try to consider it as an integer, right? We have to specify it like we have to tell it whether it is a long number or if it is a long number. So after writing the number, we have to put the L value here. It will say that it is a long number. Okay. So here, no, it is not I, right? It is L, right? Lower index is L, and it is R. And cannot find symbol MSG. Okay, sorry, MSB it is. Yes, logic conversion from double to int. Okay. So if we consider this thing, try to put it in as brackets, then we can get cannot. Oh, sorry for the MSP. Okay. How many MSs? I should have changed the whole thing MSG here instead of changing everything to MSP. Okay, now this is accepted. So if I submit it, I try to submit it. So it is accepted solution, right? So uh, the time complexity of the solution is like, now we will analyze the time complexity. Okay, now uh, for doing binary search here, it will be log n, right? For binary search, for binary search, it will be log n, right? And for calculating the for calculating the uh, price here, for calculating the price value, we are, for calculating the price, we will be going from we will be going from um, for suppose if we are like, this is a logarithmic solution here for calculating price. It is also a logarithmic approach. Um how can I say is, because from 13, for example, if you are considering 13 here, so from 13 we are going to, where we are going, 13 minus 8, that is 6. Okay, from 6, from that 13 minus 5 is 5. From 5 we are going where, it is going to 1. So we are actually decreasing it by how much difference, 8 difference, 4 difference. So in this way we are decreasing, right? So 2 4, like for example, in for example 16, 8, 4, 2, and 1, right? In this way we are decreasing it, right? So in this way we are decreasing. So what is this thing? So what is this thing? So this is a logarithmic of this is a logarithmic approach only, right? So if we consider 16 as an answer, if we log it, so what we will get? So log of 16. So what we will get? 2 to the power of 2 to the power of 4, right? Okay. So uh, here 4, so 4 into log 2 base 2, right? So log 2 base 2 will be 1. So we will be getting answer as 4. Okay, this is a logarithmic approach here. Okay, so instead of this recursive solution is also a logarithmic time complexity. Okay, this uh, solve function also x log of n to calculate the price of num. Okay, so overall complexity will be log n into log n, right? So the overall time complexity will be 2 into log n here. Okay, this is the time complexity of the approach here. And coming to the space complexity, here the recursive space also will take place, so it will be log n. Okay, how many recursive calls we are taking? We are considering log n calls, right? So this will be space complexity will also be space will also be log n. This is the overall approach here, and this is the overall intuition here, and this is the solution. And okay, this is the solution here. Thank you.